at this. Force compression. I'll put my compression here. Centimeters by force in kilonewtons. Make sure you're aware of that. 0.2, 0.3, 0.4. Well, this is messy. 0.5, and I'll just go up in compressions of 5, 5, 10, 15, 20, 25, 30. Okay, so 0, 0. So we have, goes through our origin, 1 kilonewton, we've got 4 centimetres, so that's about there. 2 is 10, that's right on that intersection there. 3 is 16, just over that there. 4 is 20, 5 is 25. Okay, plot force of compression graph on the grid provided, draw a line of best fit. This will be good. This could be anything. Yeah, alright. Well, luckily for you, the points are very, very close to all lining up. So, the line of best fit just goes through them. Okay, determine the spring constant of the spring and include an appropriate unit. There's a couple of ways we can do this. Is mathematically, or using a formula, we know F equals Kx. And the force, for example, here is 500 K, and we know that with 500 newtons applied, it is compressed by 25 centimetres, which is 0.25 metres. 500 divided by 0.25 equals 2,000 newtons per metre. That's one way of working it out. The other is to take the gradient of the graph, and it goes through the origin. So we can do rise over run, and 500 newtons divided by 0.25 centimetres. Okay, yes, I can take these points because rise, it's this minus 0, and the run is that minus 0 because it goes through the origin. So either way, gets us to do the same calculation that obviously gives us the same value of 2,000 newtons per metre. In a particular scenario, a dodgem car collides with the guardrail at 3 metres per second. Given the dodgem car and the driver weigh 100 kilos, determine the maximum compression of the spring. Okay. Alright. Now, we also have found the spring constant for this spring. Alright, so using this information I can find out how much energy is going to be absorbed by the spring. So maximum compression, we know that it's coming in at 3 metres per second, so kinetic energy is half mv squared, so that's half times by 100 times by 3 squared, so 50 times by 3 squared is 9, there's 450 joules. Okay, so that's the amount of kinetic energy the dodgem car comes in with. Now, as the spring compresses, all of that kinetic energy is going to be turned into elastic potential energy. So the elastic potential energy is a half kx squared, and so all of that is going to get converted into that as the spring compresses. So if you want a poorly drawn diagram, I'll help you out here. So just before the spring is compressed, this is our scenario here. That's 3 metres per second, and right, it bounces into the spring, and the spring will absorb all of that kinetic energy, and the dodgem car will be doing 0, and just after this it will get pushed back outwards. So it's absorbed 450 joules, all of the kinetic energy, half times by 2000 times by x squared. 450 equals 1000 x squared, divide both sides by 1000. 450 divided by 1000 is less than half, it's 0.45, and the square root of 0.45 is 0.67 metres. Now I think, yes, give it in centimetres, okay, which equals 67 centimetres. So that's saying that the spring has reduced in length from here to here by 67 centimetres. Question 13. The maximum force the occupants of the cars are allowed to be subjected to is 450. Is the spring in question suitable for stopping the occupant? Okay. So for question 13, first of all, we need to find force. We're going to have to use Newton's second law, F equals ma. We know the mass is 100 kilos. We don't know force and we don't know acceleration, so it's this that we need to find. We know the initial velocity of our cart was 3 metres per second. We know that once it's fully compressed the spring inwards, its velocity will be 0 metres per second. Acceleration is a question mark, and we know how long the distance it takes to do that, because we just worked that out at 67 centimetres. So we do v squared equals u squared plus 2ax, v squared equals u squared plus 2ax. V squared is 0 squared equals 3 squared plus 2 times a times by 0.67. 0 equals 9 plus 2 times 0.67 is 1.34. 1.34a minus 9 equals 1.34a. A equals minus 6.7 metres per second. Okay, minus, does that make sense? Well, it does, because the initial velocity of our cart was 3 metres per second in this direction, and I called it, that's obviously positive, not negative, so this direction is positive, so therefore the acceleration is in the negative direction for this situation, which is this. Okay, so what that's saying is that the cart and the occupants experience deceleration. Well, if it starts off doing 3 metres per second, then ends up doing 0, then it's gotten slower, it has decelerated. So now we do F equals ma, the force is the 100 kilos times by the acceleration of 6.7 metres per second, so that's 670 newtons, and 670 newtons is more than the maximum force allowed, which is 450. So therefore, is the spring suitable for, therefore not. It's not a suitable spring. Car's travelling around a corner of a radius of 25 metres, driving at 20 metres per second, and has a total weight of, I think that should probably read mass. Well, it's in kilograms, so it definitely should. There's another mistake in here. What's the centripetal acceleration acting on the car driving around the corner? Centripetal acceleration is equal to v squared over r, and therefore that is 20 squared over 25, which is 400 divided by 25, which is 16 metres per second. Done.